Welcome back. Today we're going to have a quick little look at water and why water is so important. Water is a lot of fun. Just ask my dog. This is Luna, and she loves the water. She'd spend every minute in it if she could. But water's important. Water is absolutely essential to life, and not just to dogs. I've shown you this slide before, but it is a really cool animation, so let's take another look at it. Once again, on the top and bottom, we have water. The water molecules are shown as white hydrogens and red oxygen atoms, and the water's in constant motion. The water molecules are forming hydrogen bonds with the water molecules around them and breaking them as they move and forming new ones. And that's happening very, very quickly. Between the water, top and bottom, we have what's known as phospholipids. And we're seeing them arranged the way that they're arranged in a cell membrane. The yellow part of the phospholipid is referred to as the hydrophilic head. And we'll talk about what that means in a moment, but basically it interacts with water. That yellow part is made up of charges. So there's charges on the surface. That part of the molecule is polar, and it can interact with water by forming hydrogen bonds. The part in the middle, the green part though, is hydrophobic. And as we'll see, that means it doesn't interact with water because it's nonpolar. That green part is nonpolar. It doesn't have any charges that can interact with the water molecules. And once again, we do have that great big blue protein in the middle, which is a channel that allows the water to move back and forth. And just as a very quick refresher here, remember that we have a few different types of bonds we've talked about. A covalent bond is where a pair of electrons is being shared between two atoms that make up a molecule. We can have a single pair being shared, that would be a single bond. We can have two pairs being shared, that would be a double bond, etc. But remember that the electrons are not always shared equally. The fact that the electrons are being shared is what holds the atoms together, but in a polar covalent bond, they're not being shared equally. And that causes this dipole to occur. I'm not going to worry too much about that word. You've probably heard that in chemistry, but it means that there's a charge differential. The part of the molecule that pulls the electrons closer becomes slightly negative, and that's what that squiggle means. It means slightly. Well, the atom that has the electrons pulled away becomes slightly positive. In a nonpolar covalent bond, the electrons are shared equally, and we don't have this charge distribution that we see resulting from unequal sharing of electrons. In water molecules, that unequal charge distribution sets up what are called hydrogen bonds. So within water, we have a hydrogen bond occurring between the hydrogen of one molecule and the oxygen of a second molecule. And water can also grab onto other polar molecules like ammonia that you're seeing here. So in that case, the nitrogen is slightly negative, and the hydrogen, of course, is slightly positive. We also have van der Waals forces, and van der Waals forces are really important on very large molecules. They can help hold large molecules together. Both of these forces, hydrogen bonds and van der Waals forces, are fairly weak, but there tends to be a lot of them. And we'll see that that's really important in DNA, for instance. There's lots of hydrogen bonds that occur within a DNA molecule, and even though each one of those bonds is weak, the overall molecule is quite strong. I know I'm really harping on this, but water is really special, and it all stems from the fact that this molecule has that charge differential, again because the electrons are held closer to the oxygen, and it also has to do with the shape of the water molecule. It's bent, and that leads to some interesting interactions as well. Each and every water molecule, if it could, would interact with 4 other water molecules. Now that's not always possible. In fact, it's not usually possible because water is moving around and those bonds are breaking and reforming. It is possible in ice though, as we'll see. Ice really is crystalline water. So I've come up with 6 properties or characteristics of water that I think make it really special and make it able to support life. And we'll go through each of those. The first one is pretty obvious. Water is really good at dissolving things. If we take something and we put it in a liquid and we dissolve it, we refer to that liquid as the solvent. And what we've added is called the solute. So in this example, we're taking salt, sodium chloride. That would be the solute, and it's being added to water, which would be the solvent. Ordinary table salt consists of 2 ions. There's chloride ions and there's sodium ions. And because they have different charges, they stick together. And ionic bonds are very strong. I think I mentioned this before, but in a dry situation with no water, they're the strongest bonds there are. So they can be even stronger than covalent bonds. However, if we put this in water, it falls apart. And for biology always occurs in water. Cells contain water. All the reactions that are important for life occur in water. And in water, covalent bonds are stronger than ionic bonds. But in a dry situation, this is a very, very strong structure, this salt crystal. You can make them yourself pretty easily. You can take table salt, you can dissolve it in water, and then take a string and dangle it in that glass of salty water for days or weeks or months, and you get crystals like this forming. You can do that with sugar too, and it tastes better. But anyway, a block of salt consists of this very regular arrangement of sodium and chloride ions. But when you throw the salt into water, it disassociates into positive sodium ions, so those are cations, and negative chloride ions, or anions. And there's actually a shell of water that forms around those ions, and then those water molecules interact with each other. So we would have hydrogen bonding between the oxygens of the water and the sodium, and I won't draw all of it, but there would be hydrogen bonds here in the middle, for instance. And then we would have hydrogen bonds between the hydrogens of those water molecules and the oxygens of adjacent water molecules. So the salt is ripped apart, and we have these interactions that maintain the ions dissolved in the water. And similarly for the chlorine ion or chloride ion, we have hydrogen bonding between the hydrogens and the chloride ion. So the salt crystals are completely ripped apart into sodium and chloride, and water does this very quickly, very effectively. If you add a little bit of heat, it's even faster because that gets the water molecules bumping around more and they bump into chloride and sodium more often. But this is a very, very quick reaction, as you're no doubt well aware. And water is so good at dissolving things, we often refer to it as the universal solvent. There's other solvents out there like ethanol, for instance, but they're not quite as good as water. Water can dissolve things so long as they're polar molecules and they have at least partial charges on their surface. They can even grab onto things like what you're seeing down the bottom here, giant proteins. So on the bottom there, we've got a great big protein. All the little bumps are individual atoms. And if there's some dipoles, some slight charges, or full-on charges, water will interact with that and hold the protein in the water so that it can do whatever it needs to do. And as I've mentioned before, all the important biology reactions happen in water. They're helped along by enzymes, as we'll see, and enzymes can also dissolve in water. They don't break down, but they're being held in the water. Fairly large molecules like glucose can be suspended in water due to the hydrogen bonding as well. So what you're seeing here is a molecule of glucose, a type of sugar, one that's really quite important in your body. And what we've got, if we look at the second diagram here, we've got places where there's a hydrogen and an oxygen together, and that's kind of sticking out on the surface of the molecule. And what happens is the electrons from the hydrogen are pulled towards the oxygen, and the hydrogen becomes very slightly positive. And the same thing down here and here, etc. So there's lots of places here where we have a dipole that can create a hydrogen bond with water. Now, not everything dissolves in water, of course. As you probably know, oil and water do not mix. And what you're seeing here is vegetable oil, and it's floating on top of the water. If we look at the structure of that oil, it's comprised of a long chain of carbons attached to hydrogen. Because carbon and hydrogen has pretty much the same electronegativity, the electrons are shared equally, and this is a non-polar substance. There's nowhere for water to latch on. There's nowhere for water to make hydrogen bonds, and that's why the oil and the water do not mix. Hydrophilic molecules are molecules that like water. Philic means to like or love. Hydro is water. So these molecules are attracted to water, water's attracted to them, and the water will grab onto them and dissolve them. Hydrophobic molecules, on the other hand, are nonpolar, and what you're seeing in this diagram is an oil again. It's actually a fatty acid. We'll talk about that later, but we've got a long chain of black carbon atoms and then white hydrogen atoms coming off of that. The electrons are shared equally in that molecule. It doesn't interact with water. If you take something like that and you throw it into the water is quite happy to interact with itself, and you can see the yellow hydrogen bonds, but it won't interact with the hydrophobic molecule. So the hydrophobic molecule gets pushed out of the way, and eventually all the hydrophobic molecules get pushed together, and that's how we get things like oil floating on top of water. Alrighty. Water dissolving things and doing it very effectively is really important. That's one of the most important characteristics of water. But we'll look at a few more. Cohesion. Cohesion is where we have molecules that are the same sticking to each other. So two water molecules that are attracted to each other, that would be an example of cohesion. And water is very cohesive. It sticks to itself really well, again, because of all that hydrogen bonding. If we look at the surface of the water, though, in a glass or on a pond or whatever, something kind of interesting happens. So at the top of the water molecules can attract to water molecules next to them and to the ones beneath them, but there's nothing above them to grab onto. Right? There's air above. There's no water molecules for them to grab onto and form hydrogen bonds with. So we get a whole lot of hydrogen bonds that kind of line up parallel along the surface. And this creates tension. It creates what's called surface tension. It's kind of like a trampoline. If you're small enough, like that little spider there, you can stand on water and you can see that it's actually pushing down on the water. It's making little dimples on the water. I love insects, and one of my favorite insects is the water strider or pond skater. It's got a few different names, but you've probably seen these before. They can stand on top of the water. And the reason they can do that is because their legs are covered with a wax-like substance, a substance that's hydrophobic. So when they stand on the water molecules don't hydrogen bond to their feet. They don't stick to their feet, but they're sticking to each other, and that creates this trampoline-like surface that something very small can stand on. They're interesting insects. They walk along the water or skate or slide or glide, however you want to describe it, along the top of the water. And when they find a dead insect, they have a little beak that comes out. It's actually like a hypodermic needle. They stick it into that dead or dying insect and they suck out all its juices. And that's what you're seeing in the top corner there. So that poor moth that it's eating, it's not hydrophobic. It has hydrophilic surfaces on its wings, and when it touched the water grabbed onto it and pulled the moth in, and then this guy came along and got free lunch. The other thing they do that's quite interesting is they communicate using the surface tension. So they'll kind of bob up and down, jump up and down, do a little dance, and create little waves, and that's how they communicate with other water striders. So you can see down the bottom there, two that have found each other, and they're in the process of making more water striders. They also bounce up and down and create little waves that bounce back off of things that are on the water, like food, and they use that as kind of a sonar. They're pretty cool. Water molecules can stick to each other in very long chains. So for instance, if you're using a drinking straw, you're creating suction, and that's pulling up the water, but the water is pulling up the water below it, in part due to cohesion, due to hydrogen bonding. It's pulling up a big long chain of water molecules. And that happens in plants. So in trees, they have to carry water a long way, from the roots all the way up to the leaves. And that can be a huge distance, and they don't have pumps, they don't have a heart or anything like that. What happens is water evaporates in the leaves, and as the water leaves, it pulls the next water molecule up. That pulls the one beneath it. So we have this long chain of water molecules that's being pulled up by evaporation at the top of the tree. And in the wood of a tree, we have these water conducting cells. They're known as xylem cells. You might have heard of those before. And they work just like drinking straws. They pull up chains of water molecules. Our next property is very similar. This is adhesion, which is where two different things stick to each other. So water sticking to glass, for instance. So glass has slight charges on its surface, and it can form hydrogen bonds with water. And that's why if you look at, let's say, a test tube, and you look at the surface of water in a test tube, it curves up on the sides. So this is adhesion. We have water molecules that form hydrogen bonds with the glass, and that pulls the water up the edges of the glass a little bit. If you've done any chemistry, maybe in high school, you might remember that when you're trying to measure something with a graduated cylinder, you make sure you hold it up at eye level so you avoid parallax. Don't worry too much about that if you don't know what I'm talking about, but you probably heard that word before. And you'll note that the water curves up. It's being pulled up the glass, and if you're measuring something in the lab, you always want to measure the bottom here, the lowest point. Now, interestingly, to the left of that, we've got two vials, and one of them contains water. And it's doing that thing we've talked about, adhesion. It's getting pulled up on the side. The other one is curving the other way, which is odd, and that's because it's full of mercury. Mercury is an element, but it doesn't have these properties that water has. It doesn't form hydrogen bonds. In fact, the glass is going to cause a bit of resistance, and it actually curves the other way. It doesn't climb up the edges of the glass. The next unique property of water is kind of a strange one. Most substances, when they go from liquid to solid, they shrink. They become more dense. So those atoms are packed into a smaller volume. So for instance, mercury, like we just talked about briefly, it's an element, it's a metal, It's liquid at room temperature. If you heat it up enough, I think it's 360 degrees Celsius, it turns into a vapor, into a gas, a rather noxious one. And if you cool it down enough, down below minus 40 degrees Celsius, it turns into a solid. So you can solidify mercury, and when you do that, it shrinks, it becomes more dense. Water does the opposite. So just like mercury and most compounds and elements, there are three phases. So the one phase would be ice, second phase would be water, third phase would be gas or vapor. But when water goes from liquid to solid, it expands. It becomes less dense. And the reason for that is, once again, hydrogen bonding. So when the molecules slow down sufficiently, they'll take a very ordered arrangement. And they actually get forced apart a little bit. And they form this crystal structure. And this is the reason that ice will float. It's also the reason that animals that live in the water can survive the winter. So we have cold winters in Canada, of course, and if ice didn't float on top of liquid water, then a pond or lake would freeze from the bottom up. And any fish or any amphibians that are hibernating at the bottom, they'd have a hard time. So again, we have these three phases. We have solid, liquid, and vapor. And I should point out that the vapor phase, the gas phase of water, you can't actually see it. So we're talking about the water that's in the air right now that you're breathing in. When you see clouds, you're actually seeing droplets of water. But there's vapor around the clouds. Now, when water is in a liquid state, the molecules are moving. And as I mentioned, the hydrogen bonds are constantly breaking and reforming. But when we go to that solid state, things slow down enough that we get more permanent hydrogen bonding, forming this regular arrangement in the ice. So it's nice that things work this way. Otherwise, everything that lived in a pond or a lake would probably be killed over the winter. And it's also the reason you don't need scuba equipment to play hockey. Yeah, if this wasn't the case and water behaved like mercury, the fish would be up the top and this poor guy and the ice would be at the bottom. We have two more properties to look at. Two more things that make water strange and magnificent. And yes, you guessed it, they're both due to hydrogen bonding as well. The first is specific heat. And without getting into a lot of detail and equations and so on, specific heat refers to the amount of energy required to raise the temperature of 1 gram of any substance by 1 degree Celsius. Let's say we took some heat energy and we used it to warm up a piece of metal. We could get that metal quite hot pretty easily. If we took the same amount of energy and put it into the same volume of water, the water wouldn't get nearly as warm. Temperature is just a measure of how fast things are moving, how fast molecules are moving. And when we heat up water, the hydrogen bonding offers some resistance. So in order to get the molecules moving, we have to break those hydrogen bonds and loosen things up. This means you can put a lot of energy into water and it will store it. So I grew up around the Great Lakes. I grew up in Toronto on Lake Ontario. And if you live on the shores of the Great Lakes, you know that your winters are going to be a bit milder than they would be away from the lakes, and your summers are going to be a bit cooler. And the reason for that is that over the summer, the water in these big lakes stores a lot of energy, heat energy, and then that's released all through the winter, keeps things a bit warmer. And the opposite happens in the summer. The lakes stay cool during the summer. Now, if you travel away from the lakes, so my parents had a cottage that was just about a 3-hour drive north of Toronto, it's much colder. The winters are much, much colder because you don't have that effect, that cooling effect and heating effect of the lakes. To be more technical, Temperature is a measure of kinetic energy. Basically, if you take a thermometer and you put it into a glass of water, what the thermometer is measuring is how often water molecules collide with it and how fast they're going. So the kinetic energy is the result of the speed and mass of the water molecules bumping into the thermometer. If you heat up that water, what you're doing is you're pumping energy into the water and you're making those water molecules move more quickly so that within a second, more of them are going to hit the thermometer. And also, of course, they're moving faster, and that registers as a higher temperature. But once again, we have that hydrogen bonding, and it kind of gets in the way of this. It takes a lot more energy to speed up those molecules because we have to break those hydrogen bonds. Now, to evaporate something, what you do is you heat it up to the point where the molecules are going so fast that they leave the liquid. So if you boil some water, what's happening is some of the water molecules are moving so quickly they jump out of the pot that you've got the water in, and they jump into the atmosphere and they become vapor. And it takes a lot of energy to do that too, to get things moving that fast and totally break those hydrogen bonds. And that brings us to our very last property that we're going to talk about. And it's very similar to the one I just talked about. Water has a high heat of vaporization. And heat of vaporization is the amount of energy you have to put in to change 1 gram of a substance, so water in this case, from liquid to gas. So again, we have to get the molecules moving really fast so they can leap out of the water and into the air. And that's why being wet is very cooling in the summer. So the reason we sweat is we release water, of course, onto the surface of our skin. The energy that's needed to heat up the water molecules comes from our bodies. So that sweat draws energy out of our body and cools our body. And that energy goes into warming up the sweat and then turning it into vapor, so evaporating it. Hopefully that gives you a bit of insight into how wonderful water is and also how weird it is. We don't think of it as weird because, of course, water is the liquid that we're most familiar with. It's everywhere on Earth. And we're very lucky that it is because, of course, water is absolutely necessary for all the things that life does. So in this little diagram here, you're seeing a cell that's eating some macromolecules, some big molecules, carbohydrates, lipids, proteins. We'll talk about that in our next topic. That stuff is being broken down inside the cell. All of that is happening in water. Things are taken apart and put back together in water. We are very lucky to live somewhere that water is so common we take it for granted. Let's compare our planet to some others. What you're seeing here on the left is Venus. Now there's lots of water on Venus, but it's all boiled and become vapor. So there's thick, thick clouds. There's lots of carbon dioxide. It's basically a runaway greenhouse effect. Of course, we're kind of concerned about carbon dioxide increasing in the atmosphere on our planet because it could warm up the planet. And that's what seems to have happened to Venus. Venus is incredibly hot. There's thick, thick clouds that contain water and sulfuric acid and all sorts of other nasty stuff. But there really isn't much in the way of liquid water, if anything. Like I said, as soon as it touches the surface, it boils away. Looking on the other side of the Earth, and the Earth is the one in the middle. Anyway, looking on the other side of the Earth, we have Mars. And there's water there, but it's ice. So ice is not nearly as accessible to living things. It is possible, though, that there might be some simple life forms, maybe something similar to archaea. That's something that's very similar to bacteria. There might be something like that, and it's kind of an exciting time to be around because we might discover something, some simple life on Mars in the next few years. But in the past, there was actually liquid water on Mars. There's lots of evidence that long ago there was liquid water on Mars. So what you're seeing here appears to be a dried up riverbed that's probably millions of years old. So there is water there. Like I said, there's lots of water at the poles. You can actually see polar ice caps, but currently there's no liquid water. If we don't find life, who knows? Maybe we'll find some microscopic fossils of life that used to exist on Mars. Exobiologists, those are people that study the possibility of life on other planets. So they're part astronomer, part biologist. When they're looking at our solar system and when they're looking at other solar systems, they're looking for planets that are in this thin zone, this distance from the sun or their star, where water can exist as a liquid. Because that's probably going to be the only place we're going to find life. So we can see Earth is well within that zone and Venus and Mars kind of on the edges. There's some other planets here that have been discovered fairly recently around other stars, and we can get a bit of a glimpse through telescopes and radio telescopes, hints at what's found in their atmosphere, and some of them do seem to contain a bit of water. Before we move on, one more basic thing about water, and a bad pun to boot. Water can be acidic, neutral, or alkaline. And we'll talk a little bit about what that means. So water can break apart. It can dissociate or break apart into a hydrogen proton and what's called a hydroxyl. A hydroxyl is just an oxygen and a hydrogen stuck together. Remember that the hydrogen atom consists only of one proton and an electron. There isn't even a neutron in hydrogen, which is kind of weird, unless it's deuterium or tritium, but we're not going to worry about that. Anyway, when water breaks apart, it releases these hydrogen protons. And they can be destructive because they can grab onto things that are negatively charged, and they might change the shape of a molecule by doing that. What will happen is the hydrogen protons that are released will bounce from water molecule to water molecule. And for a very brief period of time, they might form something called a hydronium ion, which is H3O. You can see that down the bottom here. So hydrogen protons are constantly breaking off of water molecules, rejoining other ones, then they break up, etc. This is happening incredibly quickly. If we have a solution that's acidic, that means we have more hydrogens than we should. So we would expect 2 parts hydrogen and 1 part oxygen in pure water. So if we had a cup of pure water and we had 2 parts hydrogen and 1 part oxygen, then that would be neutral. But if we have too many hydrogen protons and they're bouncing around from water molecule to water molecule, that would be an acidic situation. An acid is something that when you add it to water, it releases hydrogen protons. So now we have too many hydrogen protons in the water. If we have the opposite, if we have too few, or another way to think of it is too many hydroxyls, if we have too few hydrogen protons or too many hydroxyls, then we have a basic solution. And a base is something that when you add it to water, it will grab onto hydrogen protons and take them out of the water, or it will split off some hydronium ions. Now pH refers to the concentration of hydrogen protons. That's what the square brackets mean. You might have seen that in chemistry. So pH is a measure of the amount of hydrogen protons in the water. And just to make things more difficult, it's a negative log. Now what does that mean? Well, if we take a look at the scale on the left, we can see that 7 is pure water. If we go up to 6, even though the number is lower, there's actually more hydrogen protons. That's what the negative part is. It flips things around. Also, when we go from 7 to 6, we're going up a multiple of 10. And that's what the log part is. It refers to a logarithm, an exponential situation. Anyway, just to simplify this, urine has 10 times the number of hydrogen protons that pure water does. Black coffee has 100 times. Tomato juice has 1,000 times, etc. So every point on that scale, we're going up or down by a factor of 10. So again, pH of 6 is 10 times more acidic, or there's 10 times the concentration of hydrogen protons compared to a pH of 7. Here's the pH scale just represented a little bit differently. We've got the concentration of hydroxyl at the top there, the concentration of hydrogen down the bottom. And basically, as something becomes more acidic, there's more hydrogen protons. Or the other way to think of it is that there's fewer hydroxyls. So there's not enough hydroxyls to balance the hydrogen protons, or you could say there's too many hydrogen protons to balance the hydroxyls. So most fluids in your body and in your cells are close to neutral. You can see your blood is slightly alkaline, slightly basic. There are some parts of the cell that are quite acidic. There are some parts of your body, like your stomach, for instance, that is very acidic. So gastric juice, that's the fluid that you have in your stomach, and it's even more acidic than battery acid, which is pretty incredible. But in most cells, the cytoplasm is going to be fairly close to neutral, maybe a little bit alkaline. Again, everything at the molecular and atomic level is in constant motion. At incredible speeds, bopping around, atoms are bouncing into each other, and hydrogen protons are bouncing from one water molecule to the next. And if we have too many, we have an acidic condition. If we have too few, to balance things out, we have a basic condition. What's an acid? An acid is something that will give up hydrogen protons. So if you take something like vinegar, acetic acid is an acid. If you add it to water, it's going to give up hydrogen protons. Now, acetic acid is pretty weak. But what about something like hydrochloric acid or sulfuric acid? Those are strong acids. They're going to release a lot of hydrogen protons. HCl, hydrochloric acid, is the acid that your stomach produces. And what happens is it breaks down into a chloride and into a hydrogen proton. And that hydrogen proton can bind to the food that you ate. So hydrogen protons are positive and they will stick to anything that's negative. If there's proteins in your meal, it'll stick to any negative bits that are sticking out on the protein and cause the protein to unravel. And once it unravels, then enzymes can get in there and rip it to pieces. So that's a good use of an acid. Generally, acids are kind of harmful. You've probably seen the sign to the left before. If you spill a strong acid on yourself, it might actually break down the proteins and other compounds that make up you and cause some damage. A base is something that either soaks up hydrogen protons, so it could be something that when you add it to water, it pulls hydrogen protons out of the water, or it could be something that releases these hydroxyl groups. It's going to cause damage too if there's any positive charges sticking out on your proteins, for instance. This is going to stick to that. And again, that's going to change the shape of the protein. It's going to unravel it or denature it. We'll come back to that term later. A salt is something quite different. So a salt is something like sodium chloride or potassium chloride. That's what you see here. Or it could be magnesium chloride. There's lots of salts. And here we have a positive ion and a negative ion, and they're being held together by ionic forces. When you throw them in the water, they just break apart. So they dissolve into the water, but they don't change the pH. That's it for today's video. It's a bit shorter than usual. I'm going to try to aim for about 3 hours, maybe a little bit less per week. If I upload a long video, I might give you some extra time to process that and watch it. So realize that if there is a long video, I might skip a day and then upload a video the following day. But again, the goal is going to be about 2.5 hours to 3 hours of me talking at you per week. This is your terminology list. These are the terms that you should focus on when you're studying and going over stuff. And again, feel free to email me and ask me questions and so on. I'm happy to answer them. I'll put up a link next week where you can reach me by Zoom. I'm actually doing tutorials with you guys and with my other students as well. And I have set online hours where you can talk to me sort of face-to-face over your phone or whatever, and we can answer any questions that you might have. Okay, so I'm going to say goodbye until the next video, and I'll leave you with another short clip of Luna the happy dog.